Okay, so the recording is now on. Yesterday we stopped somewhere here on functions. There was a small bit remaining on functions, so I want to cover that last bit on functions before we move on to talk more about the sets. So I will start from this point. So this one says if you have a function from the set x, just to double check that you can hear me, please type in the chat. If there's anyone who cannot hear me, please type that you can hear me. So that way things move on better. And if at any point you can't hear me, you also say so in the chat. Okay. No one is writing in the chat, so I don't know if that means you can hear me or not. Okay. Thank you, Samuel. So I hope you can see my screen properly, or what I'm sharing on the screen. So we were exactly at this point. So if we have a function from a set x to another set y, then we defined this set. Uh, if you pick a subset of the domain, as a subset of x, we can define a set which we call f of the capital A, this one, as follows. So it's a set of all images of the elements in A. I will illustrate this again. We did an example yesterday, but we can illustrate it afresh. So suppose we'll use a small example. Suppose this is our set, which we call capital X. And then we have a second set, capital Y, consisting of A, B, C, D, and maybe 7. So let's define a function. This one goes there. Say this one goes there. We can again we let the function act on every point in the set. Good. So we saw in the last class that the image of this function, or the range of this function, it will just be the set consisting of all the elements in Y that have a preimage in X. So if you are to the range of F will simply be this, will be the set consisting of just the elements which have a preimage. In this case, the range will consist of just the elements A, B, and C. That gives us a range of a function. That one is just repetition of what we saw yesterday. But now let's pick a subset of the domain. So let's take the subset to be these points. 1, 1, and 2. So here we have picked a subset of the domain. So we can say the following. We want to construct the image of the set A, which is denoted as F and the round brackets A. So how do we build this set F of A? We simply pick the images of all the elements in A and list them out here. So 1 is an element in our subset A. So we find out where is 1 sent by the function. It's sent to A. We write it out. The other element in our function is 2, in our set rather, is 2, and 2 is sent to B. So this is now the image of the subset A. And that's what this notation will mean. So this is just a statement I've made. We say that f of a is the image of a under the function f. So I hope that makes sense. If you have any questions, please post them in the chat so that it's better to deal with the questions as they arise, because sometimes you may forget the question that you wanted to ask. So we can make it as interactive as possible. If you have any questions, please type in the chat so that we can respond to them. So now the second set that we want to define is what we call the pre-image of a set. So, but this time we pick a subset of the codomain, and then we define these sets that we call the pre-image of a subset of the codomain Y. So if you pick B as a subset of Y, the pre-image of B will simply be all the elements in X that are mapped onto some element in the set B, right? So we're going to do that again with the same function. We'll illustrate that with the same function. I will just delete this. I don't know whether I need to delete this or you. So one thing that will make this useful for you is the number of things that we are writing out that are not originally in the set of notes. As I write them out, I may end up deleting them, so they will not be available later. But you can still watch them in the video. So, but what I propose is if you're able to write some of the extra things that we do on the board as we go along, that will be helpful. So it's good to have a notebook so that you can write out some of these things to help you understand some of the concepts better. So that is my suggestion. So let's go to the other example now, where we want to find the pre-image of a set. So if I pick a subset, now I need to pick a subset of the codomain. So if I pick the subset, I can pick just A and C. So I can call this subset B, and B is clearly a subset of Y, not subset of Y. So what we want to find is a pre-image of B, what we define as F inverse. This is not really the inverse. This exponent up here is supposed does not mean that the inverse exists, but it's a notation that it's used to just find a pre-image of a subset. So the function, even if a function is invertible or not, it's always possible to define this pre-image of a given subset of the codomain. So now we go to the set. It's the set A and C. So when we pick on A, we need to find all elements from X which are sent to A. In this case, we have 1 goes to A, 3 goes to A. So those 1 and 3 are both pre-images of A. So we will put them there. The pre-image of it will include these two. So the other one that is in the subset of the codomain is C. So again, we figure out where C is and check what are all the elements in the domain that are sent to C, and it's only 4. So that covers a pre-image of B. I hope that makes sense. So we may use this later as we are working with the linear transformations and so on. So this is called the pre-image of B under the function f. Oh, thank you. Yeah, I think someone was blocking the content. Just be aware of where your cursor is so that you can you know whether when you're blocking the content or not. So this is the comment I just made earlier, that this set is does not mean that the function is invertible. The function may not be invertible, but we'll still be able to define this set. Okay. I've done it for a fairly simple situation, but I think as we go along, we will have more interesting examples. The main idea here is to understand what these definitions mean and how you can use them. We shall be using them along the way. So the next topic we shall look at is finite and infinite sets. We'll do some definitions. So we start with the definition of a finite set. So if you have a set S, we say it's finite if there is some natural number n such that we can find a bijection between the set S and the numbers from 1 all the way up to n. So if you can find a one-to-one and onto map from a set to this set of natural numbers, then we say that the set is finite. If that is not possible, we say the set, it is an infinite set. So if you can't find a bijection from the set to a finite subset of the natural numbers, then we say the set is an infinite set. We'll probably give some examples of this as we go along. So there's the other concept which we say we talk of as countably infinite. So we say that a set is countably infinite if there's a bijection between the set and all the set of natural numbers. So here the set of natural numbers is an infinite set, but you can count the numbers. And if you have a bijection from a set to these natural numbers, then we say that the set is countably infinite. So an example of a countably infinite set is a set of rational numbers. We will not prove that here, but you can look it up. Another example is a set of integers. It's a countably infinite set, and so on. So we'll say that a set, so countable will in general refer to either finite sets or countably infinite sets. So if any of these apply, then we say the set is countable. So we may or may not use this a lot, but it's a good thing to keep in mind, or no. So this gives what we have talked about. The countably infinite sets are infinite and countable, but there are also many other infinite sets which are not countable. So for instance, the set of real numbers is not countable. Also I think the set of transcendental numbers is also not countable. Just the other day we were celebrating the International Maths Day, also known as a pi day. Pi is a transcendental number, and the set of transcendental numbers is not countable. Okay, so I hope you're getting these definitions. We are trying to be as light as possible on this so that we just get the really important parts. So what is interesting about countable sets is that they are different. We can say there are different sizes of countable sets. So for instance, this is a set of if you think of 2n as a set of positive even numbers. So What we mean by 2n is a set of positive even numbers. So that means you will start from 2, 4, 6, and so on. Keeps going on and on. So these are all the positive even numbers. So this is a countable set, but it turns out it's a countable set that is a subset of another countable set, and it's a subset of another countable set, and all of them are infinite sets. So what is strange is that this set seems to be ideally smaller than the natural numbers, but you can find a bijection, a map that is one to one and onto from the set of natural numbers to the set of even positive numbers, integers. So the bijection is simply this: you pick a natural number and you send it to twice that natural number. This bijection is, so this will, it will be a one to one and onto function. So it means that the set of all even natural numbers or positive integers are countable. So they appear to be equal in size, but there are more elements in this set than I don't know if more is a correct word. You can put more in quotes, but in other words, there are some elements in the set of natural numbers that are not in this set. But what is strange is that you still have a one-to-one map from this set that appears smaller to a much bigger set, which cannot happen for finite sets. But we that is just food for thought for you. We will not go into details of that. So if you have a finite set, the number of elements in that set is called the cardinality of the set. And we shall denote that by putting two straight lines around the set. So these two straight lines mean the number of elements in the set. And so, for instance, if our set was A and it has only these elements, let's say A, B, 1, and 7. So this one has exactly 4 elements. So how we denote the number of elements in this is we write the cardinality of A is equal to 4. It has exactly 4 elements. So in general, if a set is finite, we usually say that the cardinality is less than. We can write that to mean that this is a finite set. So if you say the cardinality is less than infinity, this means the set is. Sometimes you may come across this elsewhere. That's what it means. So maybe one more thing I can mention. There's something I may not have covered earlier, but it may be important. There's something we call a proper subset. So what we mean by a proper subset of a set? So a proper subset simply means we denote, if A is a proper subset of the set B, we write it as A is properly contained in B. So properly contained means there must be some elements in B that are not in A. So if A is properly contained in B, it means B contains some elements that are not in A. So if these are finite sets, then it means the cardinality of B must be bigger than the cardinality of A. So I hope that makes sense. The proper subset simply, and we denote that. If we are not sure whether it's a proper subset, then we give the possibility of them being equal sets. So this is A is contained in B, but could also be equal to B. So, but this one is what we mean by a proper subset. It's properly contained in B, meaning that there must be some elements in B that are not in A. So here are some statements. We shall not prove this, but they are useful to know. A subset of a finite set will always be finite, and the rest follow the same pattern. A subset of a countable set must be countable. If you have a union of finitely many finite sets, you'll also end up with a finite set. And the union of finitely many countable sets will also be countable, as long as it's a finite number of sets that you are whose union you are getting, then this will work. So this one, we will not prove this, but it's important information. So here's an exercise for you. You can do some what you can do is some what do you call it, some research to show that the set of rational numbers is a countable set. If you do something nice and you wish to share it in class, next week you can do that. So are there any questions on that section, or can we now move to the next part? The relations. There are no questions. If you have questions, please type them in the chat so that we can respond. So now we move to the next topic. This is relations. Suppose we have two sets. Generally, we want non-empty sets. I did not specify that, but let's make that assumption that we have two non-empty sets. A binary, you can define a binary relation from A to B. The keyword is binary. Binary simply means two. You can also define an n-ary. I don't know how they normally write it. I think it should like that. If you have more than two sets, you can define an n-ary relation. If you have n sets, but we will not bother with this for now. We just want a binary relation. So a binary relation from the set A to the set B is simply a subset of A cross B. Here we don't care how they are paired, as long as it's a subset of the Cartesian product of the two sets, then that's a relation. So here's an example. Suppose we have a set A consisting of 0, 1, and 2, and another set B consisting of the letters A and B only. So we can pick a subset of the Cartesian product of A and B. We pick 0 and A, we pick 0 and B, we pick 1 and A, and we also pick 2 and B. So this is a relation on A because it's just a subset of, this is actually a subset of the Cartesian product. In this case, it turns out to be a proper subset. So such a thing is called a relation. So this subset is R. So sometimes what we do, if some books will do this, if A and B is in that subset, if this ordered pair is in R, sometimes some books will write this. They will write A, put the R in between, and put the B after. So this subset is a subset R, but this will mean that A is related to B. You don't have to use R. R seems to be the natural letter to use because of the word relations. But so some books will write this, that A is related to B. So another notation that is commonly used is you will find they'll put A, and then is tilde character to mean A is related to B. So A related to B, it means that the ordered pair belongs to this subset of the Cartesian product. And this subset is what we call a relation from A to B. So from A to B means A will be in elements of A in the first slot and elements of B are in the second slot. So if it turns out that we can also have a relation from A to itself, and instead of saying a relation from A to A, we call it a relation on A. So if these are the same set, if you have A and A here, then we call it a relation on A. So this will focus mostly on this kind of relation where it's we have the same set on both sides. So a function we saw is also an example, a special case of a relation. A relation is much the restrictions are relaxed. There are actually no restrictions. You just get you can pick ordered pairs without any restrictions. The function has some restrictions, and we saw that earlier yesterday. Like I said, there's a recording of yesterday's video. I posted it in the chat. If you wish to watch it again later, you can. This will also be available on YouTube later. So a relation from A to A will be called a relation on A. So we go to a definition. Oh, let's go back to the board. I pressed something. I think that's what it's supposed to be. Yeah, so we continue. A relation R on a set A. These are some properties a relation may have if you have a relation on a set. So the first property of the relation is reflexive, the one we look at. This means that if each element is related to itself, so that means if AA is in R for all A in A. We will look at some examples. I don't know if we I don't think I have any, but we can create some, or we can yeah, we'll do some examples to show this. So it's reflexive if A is if this pair A and A are in the relation. In other words, it is reflexive if A is related to A. If we were to use the previous notation, the other notation that you could use is this: if A is related to A. So I am more familiar with this second notation, and we may use this again at some point, that A is related to A. So that covers the property of reflexivity. So not all relations are reflexive. Let's see if we can. No, we don't have any example we can use earlier. We'll create one later. So another definition is another property that relations can have is this transitive property. So if you define a relation on A, it will be transitive if the following. Uh, I left. There's one I have not defined. I'll come back to transitive. I seem to have skipped this one for symmetric. So the definition of a symmetric relation is one where if B is related to A, then A is also related to B. So in other words, you can write it also like this: if A is related to B, this implies that B is also related to A. That's another way you can write this like that. So let's continue. That's symmetric. So we have looked at reflexive, and symmetric. Those are possible properties of a relation on a given set. So the last property we shall look at is a transitive property. If you have a relation on a set A, we say it's transitive if the following happens. If A is related to B and B is also related to C, then A must also be related to C. So if you put it in our other notation, we would say if A, so these two conditions, if they hold together, A is related to B and B is related to C. If these two hold at the same time, then this will imply that this A must be related to A is related to C. So I hope that makes sense. So a relation that satisfies all the three properties, one that is reflexive, symmetric, and transitive, will be called an equivalence relation. So if you have a relation that satisfies all these three properties, we call it an equivalence relation. So this is what I mentioned earlier, the different ways you can represent a relation on a given set. So one way is to write them out as ordered pairs. Use this or this as your notation. So here is an example. Suppose x and y are two sets and f is a function from x to y. So we'll define a relation on the set x as follows. So we'll say two elements in x are related. So this x1, because we are defining the function on x, right? I mean, we're defining the relation on x. The function itself is from x to y. So we're defining the relation on the set x, but we're going to use a function to define the relation. So we'll say x1 and x2 are related if f of x1 is equal to f of x2. So this is an example of an equivalence relation. We can check the properties. So clearly, any element, if you pick any element from the set X, you must have f of x is the same as f of x. So that solves the property of being reflexive. F of x will always be equal to f of x. So that's guaranteed. So that means we can say this relation is reflexive. X, any element is related to itself, right? So the second property is a symmetric property, which says if x1, so this one, I don't know that I should use the same letters. So suppose A is related to B. What does this mean? By this definition, how we've defined our relation, this means that f of A must be equal to f of B. But equality, if you are working with equality of, then this is the same as f of B is equal to f of A if you equality obeys that. But then by the way we have defined our function, what this means is that then B, I mean the way we have defined our relation, it means that B must be related to A. So the last one is so we have shown that the relation is reflexive. This was the first property that we checked. We have shown that it is symmetric. That's the second property that we have just checked. So it is symmetric. Now we need to check that it is transitive. So for transitive, we need to work with the following assumption. We say suppose A is related to B and B is also related to C. By from the definition of this relation, what this means is that f of A, f of A must be equal to f of B, and not only that, also f of B. By definition, this will be true. F of B will be equal to f of C. Just a minute. So f of B will be equal to f of C as well. But now f of B is equal to f of C. So it means I can replace f of B with f of C. So but then that simply means that f of A turns out to be equal to f of C. But then this is precisely what we wanted to show. This means that A must also be related to C. So this proves the transitive property for our relation. And since all the three properties have been satisfied, then this is we call this an equivalence relation because it satisfies the property reflexive, symmetric, and transitive properties. Are there any questions? There are some more interesting examples. We will probably meet some equivalence relations in linear algebra. Things like similarity of matrices and so on. Those are equivalence relations and so on. So that's the reason for introducing this topic. We will make use of this later. Are there any questions on this? No. Again, don't give up. If you have any questions, please ask. So the next, what we're going to define is what we call equivalence classes. We define equivalence classes now. That is the definition. So this is also here you have to pay very close attention. It's a bit can be a bit confusing if you don't pay attention. So anytime you have an equivalence relation, not just any relation, it must be an equivalence relation, a relation that is reflexive, symmetric, and transitive. Then you can define this concept of equivalence classes. So suppose you have an equivalence relation, you must have established first that it's an equivalence relation on a set X. So we pick an element, this small x, in the set, capital X, and define the following set. So we use this notation, the square brackets around. Some books may use a different. Some books will use the angle brackets to represent an equivalence class. Some will use these square brackets. I grew up on the square brackets, so I have a bias to that. But whichever notation you find shouldn't be a problem. Some, I think, uh, let's stick to square brackets. So these square brackets simply mean the equivalence class of X, and it's defined as all the elements in X which are is capital X, which are related to this small x. So this set as defined here is called the equivalence class of this element of the capital X. So this um, let's look at some properties of equivalence class. That is there any question on that? Does this make sense? We'll do an example at some point. I will do an elaborate example to pick out all this. So hopefully the definition is fairly clear. If not, we will make it clear shortly. So the properties of equivalence classes. One is if given any element from X, the equivalent class will be non-empty. It will not be empty because and for an equivalence relation, every element is related to itself. So as a minimum, this is true. The relation is usually reflexive, and therefore the equivalence class will, as a minimum, contain the set, the element itself. So it will never be empty. So the other one says that if you pick any element from the equivalence class of X, it means that X is related to Y. But since an equivalence relation is symmetric, that also means that Y is related to X. And that means that X, and this is a two-way implication, that X must be in the equivalence class of Y. So what this means is that if you pick any element from the equivalence class of X, then the equivalence class of that element will be exactly the same or equal to the equivalence class of X. So if I pick any element that is related to X, I can get an equivalence class by I can get an equivalence class of it's equal to the equivalence class of any other element in its own equivalence class. So we continue. If xy is an element in X, then we have two options. If you have two elements, X and Y, from the set X, then either the equivalence classes are equal. If they are not equal, they will be disjoint. So either the equivalence classes are equal. If they are not equal, they will be disjoint. So now if X is related to Y under some equivalence relation, we've already seen that the two equivalence classes, we didn't look at it in detail, but we've already established that the two equivalence classes must be equal. Any two elements that are related, they yield the same equivalence class. So that covers this part. So what has not been considered is when, suppose X and Y are not related, what happens? So in other words, if X is not related to Y, let's check what happens. Suppose the intersection is not empty. Suppose they have some elements in common. Then let's set that element to be Z. Setting that element to Z, what it means is that since Z now is in the equivalence class of X as well as the equivalence class of Y, it means it must be related to both X and Y. So these two statements will be true. Z is related to both X and Y, but applying the transitive property of an equivalence relation, these two being true at the same time will imply that X and Y are related. But that is a contradiction. So the assumption that the intersection of these two equivalence classes is non-empty leads us to a contradiction. The contradiction is that we started off with a statement that X is not related to Y, but the assumption that there's an element in the intersection of these two equivalence classes of X and Y leads us to the contradiction that X is related to Y. So this statement contradicts this statement up here. And therefore, this can't work. It can only work if, there must be no elements in the intersection. And therefore, that means the intersection of the two equivalence classes must be empty. So we will do an example to illustrate this. So what this means is that we some of these will be repeated. So suppose we get a collection of all possible equivalence classes of a relation R on a set X. Then each set in the family of equivalence classes will be non-empty. So every element will belong to some equivalence class. In particular, it will belong to its own equivalence class. So any element you pick from the set X will belong to some equivalence class. And earlier on, an element cannot belong to two different equivalence classes. So from the discussion we had earlier, where either the equivalence classes of two elements are either equal or disjoint. So that means an element cannot belong to more than one equivalence class, right? So what this means now, since every element uh, belong to some equivalence class, if you get the union of all the equivalence classes, you will recover the set X. So the union of all the equivalence classes of this under this relation, under this equivalence relation, if you get the union of the equivalence classes, you recover the whole set X. So that means you can write this. Now you can even go one step further and write this union as a disjoint union, because you can pick just a representative of all from the equivalence class, so that you guarantee that only one for each element you pick, only one equivalence class which it belongs to is included in the union. So this gives a more efficient uh, efficient expression, because now you have a disjoint union of equivalence classes. We'll do an example to illustrate all this. So V is a set containing exactly one element from each equivalence class, this capital V. So from the statement we have made, an equivalence class will always induce a partition on a set X. The reverse is also true. If you have a partition on a set X, the partition will also induce an equivalence relation on the set. So an equivalence relation will always induce a partition on a. So let me try to explain this. If you have an equivalence relation, we have seen that it will split your set into disjoint equivalence classes. So let's assume we have only 4 disjoint equivalence classes. So maybe this is the equivalence class of some element, say X, is equivalence class of some other element, let's call it T, is the equivalence class of some other element, call it P, and that's maybe the equivalence class of some other element, call it S. So we've seen that any two equivalence classes are either disjoint or equal. So it means these equivalence classes have nothing in common. That's the only way you can work it out. So it means now and since this the if you get the union of all the equivalence classes, if you get the union of all these equivalence classes, so get equivalence class, the first one we wrote is X, the next one is a T, equivalence class of T. If you get the union of all this, you recover your whole set X. The next one was equivalence class of some element P and the equivalence class of some other element S. So the union of all these should recover the whole of X. So that means you can write X as a union of all this. In this case, we have written it as a disjoint union. We will see, and we've also seen that it breaks X into disjoint subsets, sets that have nothing in common, and that means that's a partition of the set. So also, if you already have a partition, you can define an equivalence relation that is induced by that partition. But we won't work on that. So here is an example, another example. So for this one, I think we can do some more detail. Um, let's see. I think we don't have much remaining for today's class, so we can do some more detail on this one. So let's pick the set of integers. So we're going to define a relation on the set of integers as follows. For any pair of integers, a and b, we'll say that a is related to b if uh, where if a is equal to bq plus r. So r is a fixed number. Maybe I should have mentioned that. So basically, a is related to b if they have the same remainder when divided by b. By just hold on. So q and r are fixed. Q and r are fixed. So a will be related to b if a is equal to bq plus r. So they have the same remainder, or rather, b has remainder q, remainder r when divided by q. Something is not right here. What did I miss? Yeah, I think this is the case. Q and r are fixed. So anyway, no, I think let me not work with this example. Let me create another example. There's something I'm not getting right on this. I'll create another one that we can work with. So let's work with the same set of integers. So we will say that for any pair of integers a and b, a will be related to b if uh, if the following happens. If a difference between a and b is a multiple of some fixed integer, fixed positive integer, m. So that means the difference between a and b is divisible by m. M divides the difference. So this is a relation on the set of integers. So let's check if is it reflexive. So the first thing we want to check is if any integer will be related to itself. Okay. So what I can do is instead of using a general integer m, let's use 2. I think that will be more concrete and easier to explain. So instead of m, let's assume that the difference between a and b is a multiple of 2. In other words, 2 divides the difference between a and b. So is a related to a? We can check that by getting the difference of a with itself. A minus a is equal to 0, and 0 is divisible by any number, so that's fine. Clearly 2 divides 0. So yes, our property, this relation is reflexive, property number 1. So property number 2 that we need to check is that if you have an integer a and another one b, and a is related to b, this should imply that b is also related to a. So let's check this. Is this one true? So we go ahead and check. If you have if a is related to b, then that means 2 divides the difference between a and b. Or what this means is that a minus b is a multiple. You can write it as a multiple of 2. Let's call it, say, 2k. But then what this means is that you can also write b minus a as a multiple of 2. What will change now is the sign of the integer that you multiply by 2. So it's still a multiple of 2. What does this mean? It means since b minus a is a multiple of 2, it means b is also related to a. So this proves that our relation is symmetric. So the last property that we need to check is that is it transitive? So what we need to check is, suppose we have 3, a is related to b, b is related to c. So if these are true together, so these are true at the same time, will they imply that a is also related to c? If we can prove that, then we will have shown that the equivalence relation is transitive. So that's the question we want to answer. So if a is related to b, what that means is that a minus b is a multiple of 2, or is divisible by 2. So we can write it as a minus b is equal to 2k. Now, if b is related to c, then we can write this as b minus c will also be a multiple of 2. So let's say it's 2 multiplied by some integer t. Now, what we want to check is that if we use the fact that these statements are true to show that a will also be related to c. So how do we write a minus c? A minus c can be written, you can break it down as, if you write it as a minus b plus, that will still be true. A minus c can be written as this. This minus b plus b will give you 0, so you'll still be left with a minus c. But we have some information about a and b, so we can replace that with 2k, and we can replace b minus c with 2t. So again, we've been able to write a minus c as a multiple of 2 because I can pull out the 2 and have k. So I've been able to write, did someone join in or leave? I've been able to write a minus c as a multiple of 2. And therefore, this means that a must be related to c. So this confirms that our relation is an equivalence relation. So we talked about equivalence classes. So you need to pick an integer and find all numbers that are related to it. So for instance, I will take some shortcuts on this. Maybe I can delete this because, or maybe I can use a space on the side so that I don't have to delete this. So I'll move the board to this side. Now, let's see if we can construct equivalence classes. We can pick, say, a number like 0 and find all numbers that are related to 0. So the numbers that are related to 0 will be the numbers whose difference with 0 is a multiple of 2. So you can obtain those numbers easily by starting with 0 and adding multiples of 2 to 0 to get numbers whose difference with 0 is a multiple of 2. So this means the numbers that you will pick are 0, 2, 4, 6, and so on. This goes on On the other end, you have -2, -4, and so on. So it keeps going like that. We can also pick another number, say 1, and try to get the... So it makes sense to pick a number that is not in the first set. 1 is not in the first set, so that we get a new equivalence class. So again, you can find all numbers that are related to 1 by picking all numbers that differ from 1 by multiples of 2. So the numbers you'll pick are 3. All the numbers now you pick will be related to 1 because their difference with 1 will be divisible by 2, or in other words, they differ from 1 by a multiple of 2. So the next one will be 5, 7, and so on. So this goes on infinitely. On the other end, the other number that you will pick is just hold on, is -1, because they have to differ by from 1 by a multiple, then -3, and so on, -4, -5, sorry. So this goes on like that. So let's check what happens. You can't get any new equivalence classes. It doesn't matter which number you pick. The reason for that is that all the numbers have already been slotted in one of these equivalence classes. So to see that all the integers have been covered, you can start from 0, you go to 1, 2, 3, 4, 5, 6, 7. If you look at that carefully, you can see none of the numbers are missing. Going on the negative side as well, you have -1, -2, -3, -4, -5. If you were to continue this one, this would be -6, and so on. So you keep writing them out indefinitely. So just from this discussion now, you can see we define an equivalence relation on Z, and we've seen that it is possible to write Z as a union of these two equivalence classes, the union of the equivalence class of 0 and the equivalence class of 1. So the other thing that came out, if you pick any element from this equivalence class, it will generate the same equivalence class. So for instance, if I want the equivalence class of 2, I need to find numbers which differ from 2 by a multiple of 2. So I will start with the number 2 because 2 must be in its own equivalence class, as we saw earlier. So if I'm to pick the numbers that differ from 2 by multiples of 2, I end up with the same numbers in this set. So if I keep going to the left, I end up with the same numbers. And if I keep going to the right, I have those. If I go to the left, I will end up with this same number. So I won't get any new set. So in other words, the equivalence class of 2 will just be the same as the equivalence class of 0. The reason for that is 2 is already related to 0. So I just need to pick one representative from here. And if I get the equivalence class of that one representative, I will get the same equivalence class as that of 0. I can do the same for 1. If I pick any number in here and try to get the equivalence class of that number, it turns out to be the same as the equivalence class of 1. So if I pick 0 and 1 as my representatives, I get a disjoint union of these two equivalence classes. So you will also notice that the two have nothing in common. These are all even numbers. These are all odd numbers. So these two equivalence classes are disjoint. In other words, the intersection of 0 and 1, the equivalence classes, this intersection is empty. So these two classes are disjoint. So that means we have induced a partition on the set of integers using this equivalence class. So we've been able to illustrate an example of an equivalence relation, and we have also constructed the equivalence classes, all the possible equivalence classes of that equivalence relation on the set of integers. I don't know if there are any questions on that. So I will go back to the to the class. Now the nodes. So here is another example. Let X be the set of all m by n matrices over some field F. We can define a relation on this set by saying that A will be row equivalent to B if A is related to B if A is row equivalent to B. We will see what this means later. This turns out to be an equivalence relation as well. So, and each equivalence class will contain exactly one matrix, one unique matrix, which is in reduced echelon form. All this will come out when we are working on linear algebra. So here is an example of an equivalence relation from linear algebra. I won't go into details because we have not covered this yet. Again, if you have any comments, you can mention them. So I want to wind up with a review of these number systems. I will not do details. We'll just quickly review the number systems and then we'll close the class. And next week we shall start on linear algebra proper. So here we have integers. We'll talk about real numbers and briefly mention complex numbers. So the first set of natural numbers that we shall look at is the natural numbers. So these are just these integers from the positive integers, 1, 2, 3, and so on. I think you're familiar with this. So this is a set of natural numbers, or for our case, this is what we shall consider as a set of natural numbers. There's some important property of the natural numbers. It says if you have any non-empty subset of the set of natural numbers, then it must contain a smallest element or the least element, if you like. This is called the well-ordering property of natural numbers. It's useful in proving a number of theorems. So now the next set of integers we shall look at is the set of numbers rather we shall look at is a set of integers. The next set of numbers is the integers. So this adds a few more numbers to natural numbers. You realize that from the set of natural numbers you cannot do subtraction. There are no negative numbers here, so you can't do subtraction. So for instance, 3 minus 2, if you work out 3 minus 2, your answer will not be within this set. So you have to invent some new numbers, and that's the negative numbers that you add onto the set, and this gives us the set of integers. So here we are now able to do some subtraction, and any subtraction that you do will give you a number within the same set. So once you're done with the integers now will be both negative and the positives, including 0. 0 is also an integer. On many occasions, I've heard people asking if 0 is an integer. Yes, it is. It is an integer. So the next set of numbers that we consider are the rational numbers. The rational numbers allow us to do some division. So we cannot do any division here because we can do some. So for instance, if you divide 4 by 2, you will still get an integer. So some division can be done. If you divide, say, 3 by 2, then you have a problem. You don't have an integer. Now you have 1.5, numbers like 1.5. So we expand our set of numbers to the rational numbers, which allow us to do some division. And this will be the set of numbers which can be written as a quotient of two integers, a and b, where b is not 0. So this gives us the rational numbers. If you write them out as decimals, when you write out the rational numbers as decimals, you have two options. Either the decimals will terminate or they will recur. So you have seen this example. So if I write a number like 0.12, this is a rational number. This I can also write it as 6 over 5, I think, if you want to write it in the form in which we defined. Then we also have numbers like 1 over 3. which is also a rational number. But if you are to write it out as decimal, it recurs. So 3 keeps repeating itself. So if you have a number that either recurs or terminates as a decimal, so then that's a rational number. You can always express it in this form, where b is not equal to 0. So then the other set of numbers that we will consider are the irrational numbers. So these are the numbers that cannot be written as a quotient of two integers. So these are examples, numbers like the square root of 2, numbers like pi. These cannot be written, numbers like the Euler's constant e, and so on. They cannot be written as the quotient of two integers. And if you write them as decimals, the decimals do not recur and they do not terminate. That's the irrational numbers. So if you get the union of these irrational numbers and the rational numbers, then we now have our set of real numbers, which is denoted by this symbol. So the set of real numbers is just a union of the rationals and the irrational numbers. So this summarizes the inclusions. The natural numbers are a subset of the integers. Integers are a subset of the rationals, and the rationals are a subset of the real numbers. So once you have this, you still have some problem if you want to get square roots. So for instance, if I want to get square roots of negative numbers, I cannot do that. In other words, if I want to solve this problem, the real numbers cannot solve that problem for me. So to do that, I introduce, or rather we have to introduce a new number system, which makes this following assumption that we introduce some symbol I, and we say I is a square root of -1, or rather I squared will give us -1. So once we introduce this one, we can write out some new types of numbers called the complex numbers, which are written in the form a plus bi, where a and b are both real numbers, and of course I squared is -1. So this allows us to get square roots of negative numbers, and this is how you perform addition on complex numbers. If you have two complex numbers, if you add them, you simply add. So this part of a complex number is usually called the real part of a complex number, and this second part B is called the imaginary part of a complex number. So if you're going to add two complex numbers, this is how you will add them. If you multiply two complex numbers, this will be your result. The assumption is the two complex numbers we are multiplying are these ones, Z1 and Z2. So the other thing you can define for complex numbers is the magnitude. So if we get the magnitude of these first complex numbers, simply the square root of this expression, the a squared plus b squared, where a is a real part of z1 and b is a imaginary part. You can also get the reciprocal of a complex number. So this is a reciprocal of a complex number. If z1 is a complex number, 1 over z1 will be given. I think I computed it correctly. You can check it. How you compute this is as follows. So if you want to get 1 over a plus bi, you just multiply it by 1, and the one that you use is this one. You just multiply it by a minus bi over a. So a minus bi is a complex conjugate of a plus bi, and when you simplify this, you'll be left with the top part as a minus bi And the bottom part, anytime you multiply a number by its complex conjugate, you end up with this. Oh, there should be no square root here. I don't know why I have put a square root sign. I think that's that now. Yeah, the square root sign should not be there. Why did I put it there? So this is what you get. It's good I decided to do the computation. So this is the same as 1 over the complex number z1, where z1 is this complex number a plus. So this square roots needs to go. Why did I put the square root? Strange. So there you are. This is a reciprocal. So you can represent a complex number in the complex plane. So you have the imaginary axis and the real axis, and pick a complex number a plus bi as a coordinate, as these two coordinates a and b. And any complex number now can be represented as a point in the complex plane. And the magnitude would be this distance from the origin to the point AB. That gives the magnitude of the complex number, which is a square root of a squared plus b squared. You can also write it in polar form, where just using your trigonometry, this angle that this line makes with the positive x-axis, theta, will be called the argument of the complex number. And using trigonometry, you can show that a is the same as r cos theta, and b is the same as r sine theta, and therefore you can write this as r multiplied by this expression in the brackets, cos theta plus I sine theta. And this expression in the brackets now can be written as e raised to I theta. So this is called the polar form of a complex number. So this particular Q, R, and C, the rational numbers, the real numbers, and the complex numbers are examples of what we call fields. And we shall be looking at vector spaces over the field of real numbers and the field of complex numbers. That will be the next class. So that brings us to the end of this presentation. I hope it makes sense to all of you. But now we'll now jump into linear algebra, the proper linear algebra next week. I will upload the set of notes that we shall be using for the next class, I think either tomorrow or later today. So anytime you come back to this class, you'll be able to this platform, you'll be able to see the notes that we are working on. Any questions, you can type them in the chat. We can respond to them. Any comments, any questions, we will respond to them. So maybe now for this inclusion, now we can add one more. The set of real numbers is contained in the set of complex numbers. So the set of complex numbers allows us to get the square roots of negative numbers, which we could not do in R. The set of real numbers allows us to get the irrational numbers, which we couldn't get from the rationals. The set of rationals allows us to get quotients, which we could not do. We could do partially in the set of integers. And the set of integers allows us to do subtraction, which we could not do in the set of natural numbers, or rather we could do only partially in the set of rational numbers. Natural numbers, not rational. Natural. So allow me to stop the recording at this point. And please, it would be nice if we got some reactions. We want this to be as interactive as possible. And to know whether you're finding it useful. Because for you to attend this, it means it must be of use to you. But we will start on proper linear algebra next week. So what you have all been waiting for will show up on Thursday next week. The video for this will be available